All right, in this video we're going to look at more examples, but we're going to try and focus specifically on examples of integration by parts that have bounds, where we have a definite integral. Okay, so let's see, this first example shouldn't be too terribly surprising. Let's see if we let u be natural log x, and then that would mean that du is 1 over x dx. Let's see, then we get that dv is 1 over x squared dx. If we integrate that, that'd be the same as x to the minus 2 dx. So then v would just be x to the minus 1, so it'd be 1 over x negative, and that's what we get there. Okay, so then here, when we do uv, we do natural log of x times negative 1 over x, and then I would need to make sure to evaluate this from when x is equal to 1 to x is equal to 2. Subtract integral, still from 1 to 2, keep the bounds, and then, because these u's and v's that I'm using, I'm not doing u substitution, right? I'm still using x. I'm just using a symbol to help me kind of establish the formula. So then it'd be v du, so minus x, minus 1 over x times 1 over x dx. Okay, and so in here, I'll just rewrite this. So let's see, we'd have negative natural log of x over x evaluated from when x is equal to 1 to 2 plus integral 1 to 2, move those x's to the numerator to get x to the minus 2 dx. Okay, so let's see what I get. Negative natural log of 2 over 2, and then plus natural log of 0, which would be, or natural log of 1, which is 0, so then I'm just going to eliminate that. And then plus, integrate this, I'd get x to the minus 1, negative, evaluate from 1 to 2, and so then I get negative natural log of 2 over 2, let's see, it'd be minus 1/2 plus 1, so in all, I get a positive 1/2, so 1/2 minus natural log of 2 over 2 would be my final answer here. Okay? Next example. Okay? Yeah, we are going to need to do a little bit of work on this before we can actually do the u sub. So what we actually need to do is before we need to do a u sub before we can actually do integration by parts. And so the u sub that I'm going to pick is going to be, let's use a different variable. Let's use q. I don't know, just so we don't get u's and v's all mixed up. I'm going to do q is equal to, actually, let's do q squared. Do I want that one? Sure, we can do q squared. Q squared is equal to 4 plus r squared. Is that going to be fine? Sure. Yeah. And then if we do 2q dq, that would be equal to 2r dr, or dr. Okay, and this r cubed is r squared times r. Okay, and I'm just going to eliminate the 2's. Okay, so then if I rewrite this, leave the bounds for a moment, I'd have, let's see, this r dr would be q dq, so q dq. Denominator would be square root of q, which I would just say is q. Okay, and then I'd have this r squared yet, which if I solve for r squared, q squared minus 4 would equal r squared. So then I'd have q squared minus 4 in the numerator. And then now if I'm just running these things through, so put in 0 for r, I get 0. 0 plus 4 is 4, and then 1 plus 4 is 5. Okay, and so all said and told, this is, let's see, those reduce, so just q squared minus 4, 4 to 5, and then dq. Oh, look, I actually don't need to do integration by parts. So you could do integration by parts. You could, select r cubed as v and then the square root as, dv. You could do that, but sometimes there's other methods that can pop up that could be just as helpful. Okay, but the next one is actually a little bit more interesting. We haven't quite seen something like it yet. Actually, we have. This one, the t cubed, this one isn't too bad. So if you think about what you would select, you might do u as t cubed, meaning that du is 3t squared dt, and then that would mean that dv is e to the negative t squared dt. Okay, then the only challenging piece of all this is figuring out what v would be. And so this is going to be really challenging to integrate as is. And so, I mean, you could try u sub, it's not going to work, but what we can do is if we take a t from the t cubed, then this we'd have to change, right? This would be 2t dt, and then we could do something like that where it's t e to the negative t squared, and then you could do a u sub with it. So if you did like u is equal to negative t squared, then du, negative du, over 2 would equal to t dt. And so then if we integrate that, we get negative 1/2 e to the negative t squared. Okay. I went through that kind of quickly, but you can pause the video and verify it on your own. Okay. And so then what we get at long last would just be, let's see, u, so it'd be t squared, and then times negative 1/2 e to the minus t squared minus, actually plus 1/2 integral e to the negative t squared times 2t dt. And so then the 1/2s end up canceling out. And I believe we literally just did this integral, but we get, negative t squared over 2 e to the minus t squared, and then minus 1/2 e to the minus t squared, all plus c. Okay, so don't be surprised that if you see something that looks like you might have to do normal lipit with it, right, to select integration of parts, you might actually need to tweak it. But the last example that I want to do is actually one that is super interesting and super annoying. Okay, I'm actually going to modify it to make it a little bit easier for us. Okay, first I'm going to get rid of the bounds. Okay, we can do it in this format. It's just going to be a little bit more cumbersome. If you want to try the problem in its original incarnation, please do. Alas, here we are. And then I'm going to make this just e to the t. Okay? All right, so then you think, all right, so you just have u, lipit, right, li, there's no l, there's no I, there's no p, there is an e, okay, so we do that. That means that dv is going to be sine of 2t dt. Okay, so then v would be 1/2 cosine of 2t, and du would just be e to the t dt. Right? Easy. Negative 1/2. I forgot a negative there. All right, so then we move forward and say all this is equal to, let's see, be negative 1/2 e to the t cosine of 2t, and then plus 1/2 integral e to the t cosine 2t dt. Okay. Well, that doesn't integrate nicely, but I can do integration by parts again on it. Okay, so then here I would do u would equal e to the t, du is e to the t dt, and then v and dv, so dv would be cosine of 2t dt. That makes v 1/2 sine 2t dt, or 2t. Okay, so let's see, this is just going to stay out front, e to the t cosine 2t plus 1/2. And now this whole thing breaks down according to the integration by parts here. So we'd have, let's see, 1/2 e to the t sine of 2t minus 1/2 integral e to the t sine 2t dt. All right. Is that helpful? No, I mean like e to the t sine 2t, that we just need to go again, right? Actually, this is helpful because remember on the left-hand side, that's all equal to integral e to the t sine 2t dt. If I look, that is the same as in here. So I can maybe just collect like terms. Okay, so if, this is really bizarre. This is called a cyclic integration by parts example. So what I'm going to do is say, okay, we'd have, let's see, if I were to collect things over, right, multiply the 1/2 or distribute the 1/2 in, this would be 1/4, right? So if I move it over, I'd have 5/4 integral e to the t sine of 2t dt is equal to negative 1/2 e to the t cosine 2t plus 1/4 e to the t sine 2t. Okay? And so then, if I really just want to solve just for the integral, as was the original problem, right? Get rid of the 5/4 and I'm done. Okay, so I have integral e to the t sine 2t dt is equal to, divide this over, what do I get? Negative 2/5 e to the t cosine 2t, and then, let's see, I'd get plus 1/5 e to the t sine 2t. Now, technically here, I didn't integrate a thing, right? I just used integration by parts formula over and over and over, and I just rearranged it. So do you add a plus c? Do you not add a plus c? I mean, you can add a plus c if you want. It would, again, we're saying an integral is equal to that. It would differentiate out. But technically here you wouldn't have a plus c because, again, you didn't do any integration. You just rearranged it. Okay, so be on the lookout for something like that. That can pop up from time to time, this sort of cyclic process. And I know we will see one in class, so be ready.